Okay, so we've stated that if you set up a reaction, it will proceed until you reach an equilibrium, at which these things will have certain concentrations, and those concentrations then remain fixed. But that's only true so long as we don't change anything, so long as we don't introduce any extra chemicals or take anything away, or change the temperature or change the pressure. As soon as we change any of those variables, the reaction may start up again and move in one direction or the other until a new equilibrium is established. And one of the things that you need to be able to do is to make predictions about which direction that equilibrium will move in when you make a particular kind of change. Now, there are basically two approaches to that. One is a sort of slightly mathematical approach using something called an equilibrium constant, and that we'll learn about next year. But for the moment, we're going to use an approach which actually is in some ways more of a rule of thumb than sort of a proper bit of science. In other words, it's just the product of someone's observation without really having any understanding behind it. But it, on the other hand, is incredibly helpful because it always gets it right and is very easy to apply. And it's called Le Chatelier's principle. So Le Chatelier was a French chemist in the 19th century, and he was interested in all kinds of things. His abiding passion was that he was fascinated by the setting of concrete, and he devoted the greater part of his career to understanding that. But he also did a load of other things, and one of the things he did was to look at this idea of equilibrium moving to different positions, in other words, changing the amounts of stuff in an equilibrium when you change the conditions. And he noticed something which turns out pretty much always to be true, which is that when one of the conditions is altered, the equilibrium shifts in the direction that opposes the change. Okay, so as I say, it's not something he derived by having deep thoughts about what you would expect to happen. It's just something he noticed from looking at equilibria, and that's the level we're going to use it on. So next year we'll look at this with numbers and then to some extent have a sort of deeper understanding of where it comes from. But most of the time this is the quick and easy way to think about what will happen when you make a change to one of the conditions. So you need to learn that principle, but most importantly you need to practice applying it. So let's think about what it means. Okay, so what you imagine is that you have got a particular temperature and a particular pressure, and you had a particular starting composition, the reactions happened, and it settled down at an equilibrium, and so now everything stopped changing. Temperature settled down, the pressure settled down, the amounts of each substance are remaining constant. And then you decide to be awkward and change something. So let's say, for example, let's add extra SO3 to the mixture and ask what's going to happen. Well, we could try and think about that at a sort of deep level and think about the rates of the forward and back reaction. And you can see that what's going to happen is adding more of this doesn't change the rate of the forward reaction, because that depends on the concentrations of those. We haven't changed that. But it will increase the rate of the back reaction because you've got a higher concentration of that. And if you increase the rate of the back reaction, but not the forward one, it means you're going to make more of this, right? Because the back reaction is then happening faster than the forward one. And so you're going to make more of that. And it'll be a bit like the situation we had at the beginning. As some of the extra SO3 gets used up, its concentration will then drop again. So this rate which had increased will drop back down again. As you make more of these, the forward rate will increase until eventually the rates become equal again and you have a new equilibrium. But at that point you don't have the same concentrations you had to start with. So that would be a sort of way to think about what you'd expect. But Le Chatelier gives you a way of getting the answer without getting into all of that. And he just says, right, what have we done? Well, we've increased the SO3 concentration, and Le Chatelier says that therefore the equilibrium will shift to oppose that change. What does that mean? Well, it means we've increased it, so it will try to decrease it again. And obviously the way you decrease the SO3 concentration is by shifting in the backward direction. Okay, so we can describe that shift. Classically, what people do is they use the language of shifting to the left or shifting to the right. If, like me, you have trouble with left and right, and you don't always get it right when you're talking about those things, that may be a dangerous game to play, in which case you can talk about shifting in the backward direction and shifting in the forward direction, and that would be fine. That's a safer thing to do if you have left-right issues. So the equilibrium will shift to oppose this, and that means shift in the backward direction. And what does that mean? Well, what it means is, if the equilibrium shifted that way, that means that there will be more SO2 and O2 when a new equilibrium is set up. Another way we can change the position of equilibrium is by messing around with the temperature or the pressure, because those variables too, Le Chatelier applies to them. So if you change them, he says, well, the equilibrium will try to undo what you've done. So let's have a think about what happens if we increase the temperature. So what happens if the temperature is increased? Okay, so this is an external intervention. This is us saying, right, let's, turn the heat on and change the temperature in the reaction mixture. So what happens if the temperature increases? So Le Chatelier says that it will shift in the direction that opposes the change. Well, how do you oppose a temperature increase? And the answer, of course, lies in that number, the delta H. Because delta H is described as being minus 99 kilojoules per mole. When you have a reversible reaction like this, the number you quote is always for the forward process. So that means it will be minus 99 going forward, and it will therefore be plus 99 going back the other way. Okay, so that's a convention you need to know, that when you have reversible reactions, obviously the enthalpy change is equal and opposite, and the number that you quote is always for the forward reaction as you've written the equilibrium down. So, how do you oppose a temperature increase? Well, you move in the direction that takes heat away again and tends to cool things down. And of course the direction that takes heat away is the endothermic direction, because that's what endothermic means. So exothermic adds extra heat, therefore will tend to increase the temperature. Endothermic takes heat away and therefore tends to decrease the temperature. And if you remember your sign convention, remember negative is exothermic and positive is endothermic. You've got to absolutely be sure you've learnt those sign conventions. So the way you oppose a temperature increase is that you will shift in the endothermic direction. Which means that we'll take heat away and therefore oppose the temperature increase. Okay, so it's the same kind of idea as we had when we changed the concentration of a substance. But now you just have to think a little bit more and make sure you understand what the delta H numbers mean. So it's negative going forward, which means heat's given out if you go that way. Positive going backwards, which means heat's taken away if you go in the backward direction. And that's how you oppose a temperature increase, by taking heat away. And then you have to spell that out. You can't just say, oh, it goes in the endothermic direction. You have to tell people which direction that is. So that means shift in the backward direction. And what does that mean? Well, it means you'll get more SO2 and O2, but less SO3 in the new equilibrium mixture once it settles down again. So Le Chatelier's principle is very helpful because we were able to figure that out without thinking about any complicated things to do with distributions of energy and stuff, which we would have to do to actually answer this problem at a sort of deep level. We can just make the prediction based on his rule. What Le Chatelier's principle doesn't do is give us any idea of how big the shift will be. So, you know, if we increase the temperature by 10 degrees, you might think, well, does that mean that, you know, there'll now be 3 times as much SO2 as there was before, or only, you know, 1.05 times as much? You know, is it a little shift or a big shift? And Le Chatelier is silent on that. Okay, it just tells you the direction that you go in. In order to quantify that, you would need to use these numbers, which we'll learn a little bit about next year, which are called equilibrium constants. But that tends not to be the issue at A level. As long as you get the direction right, that's largely all that people are bothered about. As an alternative to changing the temperature, we could also change the equilibrium by changing the pressure. Because again, Le Chatelier tells you that the reaction mixture isn't just going to stand there and let you do that, it's going to try and shift in the direction that will oppose the change you make. So in order to understand that, you have to remember a little bit about what causes pressure in a mixture of gases. So pressure comes from the individual molecules, if you like, crashing into the walls. Every time a molecule crashes into the walls, it exerts a force on the walls, and it's the sum of those forces that gives you the pressure, or the sum of those forces per unit area gives you the pressure. So what you can see is that the more molecules you have in total in your reaction mixture, the higher the pressure will be. So the way you oppose an increase in pressure is to decrease the number of molecules in the mixture, because if there are fewer molecules crashing into the walls, there's going to be less pressure. And so that's how you oppose the change. So if we add up the total moles of gas, and we only look at the gases here, in this case there are only gases, so it's not an issue, but in equilibrium involving solids and liquids as well, because the particles in the solids and liquids are confined, they're not going to have very much impact on the pressure. It's the ones whizzing around in the gas phase that do. So what we're going to do is just count how many moles of gas there are on each side of the equation. And in this case that's easy, because you can see we've got 1.5 moles of gas on the left, but here we've only got 1 mole of gas. So what that means is that if we increase the pressure by, you know, pushing a piston down or whatever to compress the mixture, the equilibrium can shift to oppose that change by moving in the forward direction. Because if you move in the forward direction, you decrease the number of moles of gas and therefore decrease the pressure and oppose the change. Equally, if you decrease the pressure, it could shift back this way to try and increase it again and oppose the change. So once you see that connection, it's very easy because you just count the moles of gas on each side. Okay, so again, it's a Le Chatelier explanation. We're not explaining things at a deep level here, we're just applying the rule. Okay, and he says that the equilibrium will oppose an increase in pressure by shifting in the direction where there are fewer moles of gas. And so you just look at the balancing numbers in the equation, making sure you only look at the gases. And so in this case, that means that you shift to the right. Or if you don't like right and left, forward direction. Because there's only 1 mole there compared to the 1.5. And that means that you will get more SO3 and less SO2 and O2 in the new equilibrium mixture. Okay, so those are really the 3 kinds of Le Chatelier problem that you have to deal with. Changing the concentration of one of these things by injecting some of it in or removing some of it from the mixture, changing the temperature and changing the pressure. It is just worth looking explicitly at the way you can get caught out if you're not very careful. So if you just think of, oh, the way you oppose the pressure increase is to move in the direction where there are fewer moles, rather than specifically moles of gas, you might look at this and think, oh well, there's 2 moles on the left, 2 moles on the right, so actually you can't do anything. So you might predict there would be no change in the equilibrium if you increase the pressure, because it doesn't matter which way it would shift, you'd get the same number of moles. But when you look at the state symbols, you realise that isn't true, because the carbon here is a solid. So on this side you have only 1 mole of gas, 2 moles altogether, but one of them isn't gas, whereas on this side you have 2 moles of gas. And of course what that means is that if you increase the pressure, it will shift in the direction that tries to decrease it again, which is backwards, because moving backwards you have moving in the direction of fewer moles of gas, and so that will oppose the increase in pressure. So you have to watch the state symbols in these questions, and remember it's moles of gas, not just total moles, that are important when you're thinking about the effect of pressure.